Alright, so we're going to continue our discussion of the concept called optimization. You should have your blue sheet out, optimization study guide, however you want to put it. And you also should have already been given a packet of optimization problems. We'll get to that in a little bit. But first thing I want to do is I want to go through the cake pan problem that we started yesterday. And I want to go through it from the perspective of the optimization study guide. So you have that next to you. I'm going to talk about some things as I go through it. The first thing I'd say is, alright, in this problem, what is it that I'm trying to do? I'm trying to maximize the volume of the cake pan. And so that defines what I'm doing. Here's my diagram, which isn't a great diagram. You might want to draw it maybe a little bit better in terms of what your actual variables are. Here's the formula that I want to use, but here's the kicker. I want to write that volume formula in terms of the variables of the problem. And as we talked about in class, I just chose a 10 by 8 piece of sheet metal or construction paper. And remember what we said is, if I take that X inch cut out of each corner, that the dimensions of my rectangle are going to be this: 10 minus 2x, because I'm cutting it out of each corner, times 8 minus 2x times x. What I want to do right now is I want to try to simplify this. Ultimately, I'm going to take the first derivative of this, and we'll talk about that in a second. But I'm foiling out the first two problems, or first two expressions, times each other, and then I multiply that by x, and then I distribute the x through, and I get this simplified function. Now, next part, I'm taking the first derivative of this function. I'm going to say I'm taking the first derivative of v of x, the volume in terms of x. And the reason I'm doing that is, as we've talked about repeatedly through this chapter, the first derivative will help us find critical values. And critical values often show themselves as extrema, a relative min or a relative max. And so I'm going to set that first derivative that I just found, I'm going to set it equal to 0. And in this case, you might try to factor it. I don't think factoring works, so I've already done the quadratic formula on this. If you want to push pause right now and use the quadratic formula yourself, you can. Or just take my word for it and know that we get two solutions for this, 4.5 and 1.5, approximately. Now, they're critical points, but I don't know what kind of critical points they are. And so that's when we use the second derivative test. Remember, the second derivative test tells us that if we take the second derivative of a function and we plug in our critical points or our critical values, that from that we can determine what type of critical value it is. So my second derivative of this function, this isn't right. I'm going to erase that and try that one more time. Second derivative of this function is actually 24x minus 72. Alright, now I'm not going to set it equal to 0 because I don't care about inflection points. What I care about is what kind of critical values these are. So if I plug in 4.5 into this function, so 24 times 4.5 minus 72, and I get 36. Now remember, that's positive, which means that it's concave up, which makes this function, or which makes this critical value, a minimum. Now I don't really want that answer because I don't want the minimum amount of volume. I want a maximum amount of volume for my cake pan. So hopefully when I plug 1.5 in, I'll get a different answer. So now 1.5 plugged in gives me 36 minus 72, which is negative 36, which does make it concave down, which makes 1.5 a maximum value. So here's where we're kind of applying what we've learned throughout the chapter to this real life problem. And so from that, if I know that 1.5 is to be my maximum for my x, that tells me my cut I have to make in each of my corners. So to answer the original question, I'm going to create a cake pan whose dimensions are 1.5. And then remember, if I subtract that from each side of my 10, it's going to give me 7. And if I subtract it from each end of my 8, it gives me 5, and so my dimensions are 1.5 by 7 by 5, which would give me a volume of 52.5 cubic units. This is what we're going to go through for the next couple of days, working on real-life example problems, story problems that we can solve using the first and second derivative. At any point during this, please stop the video, pause it, go through it, try to figure problems out before I just walk through it with you right now. Alright, so now we're going to look at a couple examples today from your packet. So have that packet out. First problem we're going to look at right now is question number 16. Question number 16 is talking about two numbers. Alright, two positive numbers whose sum is 12. So if I define my two variables, I would say x plus y equals 12. And what I want to do is I want to solve this one letter in terms of the other. I don't really want to do implicit differentiation with these kind of problems, so I want to make sure that when I take the first and second derivative that I'm doing that with only one variable. My derivatives will be way easier if I solve it in terms of the other. So I'm going to solve this product, and if you notice I already said x times y squared because that's what the rest of the question said, the product of one of them and the square of the other. And now I'm plugging in 12 minus y for x, multiplying it through, and there's my simplified function. Taking the first derivative of that, I'm going to get 24y minus 3y squared. Looking for critical values, so I'm setting that equal to 0, factoring out 3y, and I'm going to get two solutions for this problem, y equals 0 or y equals 8. Now you might be able to kind of look at it and figure out which one the right answer is right now, but if I take the second derivative of this function, I get 24 minus 6y. If I plug in my two values, plug in 0 first, and then plug in 8 and figure out what those answers are. So when I plug in 0, I'm going to get 24. 24 is a positive number, which makes this concave up, which makes my critical value a minimum. It's not what I want. The problem asks for a maximum, so if I plug in 8 now I get negative 24 for an answer. That is a negative number, obviously, which makes my critical value a max. And so based on this, the solution to my problem, if y is 8, I can go back and figure out that x must be 4, and I could check this if I wanted to, and figure out that does give me the biggest product. Again, try to do these problems on your own before I go through them all for you. Next question we're going to look at right now is question number 9. Again, stop right now. Push pause on this before we go any further. So hopefully you've tried doing this problem before you're listening to more of this right now. And in this case now, I've got a rectangular piece of land and I've got to fence it in. I got two dimensions. Call them whatever you want, length and width or side and whatever. In my case, I've got them labeled as standard for standard fencing and heavy duty fencing. And so I'm looking at what my perimeter formula would look like right now, because I know that I'm going to have to use that fencing around the perimeter to create my rectangle, and that if I take $2 times my two sides that get standard fencing and my $3 times the two sides that gets the heavy duty fencing, that together that's going to equal $6,000. And so that's how I generate my initial equation, and now I'm in the process of solving that for h. Why h? No reason, it's the one I chose. So now I have h written in terms of s. So now I'm going to go to my area formula, because it's area in this problem that I'm trying to optimize. In this case, maximize the area. I want to know how much area can I contain given this amount of money of fencing. And so as I plug those in and plug that in place of h and now go through and simplify that function, that's the function right there that I'm going to take the first derivative of. First derivative of that is 1,000 minus 4/3 s. I'm going to solve that right now for s. That will give me my critical value in this problem. You'll see that in this problem you only have one critical value. That critical value ends up being 750. Even though it's the only critical value you have, you better make sure that's the right critical value for this problem. You better make sure that's the one that gives you a maximum. And so taking the second derivative of this just to verify that, second derivative is just going to be negative 4/3. What that means is it's always negative. No matter what value you would plug in for s, this is always a negative answer at the end, which means that this function is always concave down, which is why we only got one critical value for this, and indeed that has to be a maximum. So 750 is the total length that gets the standard fencing, and then I can plug it back in to figure out what my other variable is, and I end up getting 500. That is the length that gives me the normal fencing, or the heavy duty fencing. Last question we're going to work on together, and then I'll give you a couple of problems that you can work on your own, is question number 13. Question number 13. So again, stop this right now. Read the question, try to figure it out first. Well, hopefully you did that. Again, I'm going to label my figure right now. It tells me that I've got a square base. So I'm going to have two dimensions be the same. So in this problem, the bottom of this cube right now, it's not a cube, but like a square prism, is x by x, and then I've got a height. And I've been given that the volume of this problem is 2,000. Alright, so I'm going to solve this for h right now. And again, I do that because I think it'll be a little bit easier in the problem to do so. And now I'm going to optimize the cost of this. This is telling me what's the dimensions that have the least cost. And so the cost is going to be, it's $2 for every, or it's 2 times as much to cover the part that is the bases of this container. And so that's why that 2 comes from out in front of my 2x squared. 2x squared is just the surface area of the top and the bottom. And then the 4xh is the surface area of the 4 other sides. So again, that 2 out in front just is because you can think about it like it's $1 per square unit for the other 4 faces, $2 for every square unit of the top and the bottom. If I simplify this now and work all this out, and again I'm going to plug in right now 2,000 over x squared for my h, so that I only have one variable in this problem, and you can plug that in anytime you want, it doesn't have to be now. If I work all that out right now, I get a little bit more complicated function to try to take the first derivative of. But if you rewrite it like this, it's not too awful. Taking the first derivative right now, the cost with respect to x gives me 8x minus 8,000 over x squared. Alright, I'm going to try to set this equal to 0 now and solve this for x. And again, that will give me my critical values. So I added the 8,000 over x squared to the other side. Cross multiply, of course. You get 8x cubed equals 8,000. Divide both sides by 8. You get x cubed equals 1,000. Take the cube root of each side, and you get 10. Again, what is 10? 10 is the length in centimeters of one of the sides of the base. Again, make sure that this indeed is going to give you the minimum cost. And so as I plug in 10 into the second derivative, I do get an answer that is positive here. I think you get about 24 for it when you're done. Since that's a positive number, it's concave up, which indeed does make 10 a minimum. I can take 10 right now and plug it back into whatever function you want, probably the x squared times h equals 2,000, and that ends up giving me 20 for my height. And so the dimensions of this container to minimize the cost is going to be 10 by 10 by 20 centimeters. Alright, that's all the help I'm giving you for tonight. please work on at least these 4 problems. If you want to do additional problems, that's up to you. But at least try to do problems 5, 7, 14, and 16. It's kind of a good variety, I think, of problems, but it's some that we have talked about. But if you want to continue to do other ones, go ahead. We'll do the same kind of deal tomorrow. See ya.